Hi, welcome to physics. This is motion lesson 3, talking about falling objects. Now, when an object is considered falling, it means that there is only one force acting on the object, and that is gravity. In the previous labs that we've done in this lesson, we should have come up with the gravitational constant or the free fall acceleration, and so let's go ahead and talk a little bit about that. Now, gravity provides a constant acceleration on all objects in the same gravitational field. It's dependent on the celestial body that you're located near. If you are on the Earth, your gravity is going to, or the gravity on Earth is considerably different than the gravity, let's say, if you were able to get on the Sun, or if you're able to be on the Moon. The gravity is changing depending on which celestial body you are actually close to. It's always going to be pointed downward. So anytime we talk about the gravitational acceleration, it's always objects are always going to accelerate downwards, and you're often going to see the variable g given for that. And then in our labs, what we should have come up with is that g equals 9.81 meters per second squared, and that points downward. Now, because we have a change in our coordinate system, our kinematic equations are going to change just ever so slightly. And you should be able to understand these changes very easily based on what we've already learned in math, and especially the Cartesian coordinate system. One thing that you'll notice is that our accelerations now for falling objects is now g instead of acceleration, or an a. That's because accelerating objects all accelerate, or falling objects all accelerate at the same rate. Another thing that you'll notice is that instead of delta x's, which is my change in position, because we're talking about another dimension, we're actually going to change it to our delta y, and you'll see that really more prevalent in the next lesson when we start talking about two-dimensional motions, because we'll have to situate or separate our horizontal displacement and our vertical displacement. So we're going to go ahead and start using delta y for our vertical displacement, and those are really the only two things that you're going to notice that are different in our kinematic equations. Now, what we want to do is we want to go ahead and give you a couple examples of how to work free fall motion, and we're going to start with example 1. And on example 1, we have a rock that is dropped off of a school building and hits the ground 4.6 seconds later. How tall is the school building? Well, let's go ahead and start pulling out the knowns that I know, or that I can get out of the word problem, so I can start eliminating some of my equations. So we have a rock that is dropped off a school building. Now, whenever I drop things, whenever anybody drops things, if you're not throwing them, then that means your initial velocity is going to equal 0. Okay, and it hits the ground 4.6 seconds later. So that 4.6 seconds has to be a time. How tall is the school building? So I'm looking for my delta y. So my displacement in the vertical direction is really what I'm looking for. Now, there's some things that even though this doesn't tell me, I have to assume that g is needed. So it's going to be negative 9.81 meters per second squared. All right, or 9.81 meters per second squared downwards. Now, once I have these knowns and unknowns pulled out of my word problem, now it's time for me to start canceling some of my equations. Now I'm looking for delta y, so that means I have to look for an equation that has delta y in it. Now none of the first one does not, but the other three do. Now I want to look at, well, what do I know? Well, one thing I don't know is the final velocity, or the velocity of the object when it hits the ground. So all of these with the final velocities are now gone, and I'm left with just one equation to solve for the delta y, or my vertical displacement. Now, delta y is going to be equal to VIY, or VIT, plus 1/2 GT squared. So filling in, I know that my initial velocity is 0. So that whole term is 0. And I'm going to be left with 1/2 times negative 9.81 times my time squared. So that's 4.6 seconds squared. Now let me go ahead and grab a calculator real quick. And I'll type this into my calculator as 0.5 times negative 9.81 times 4.6 seconds squared. And I'm going to get delta y equal to 103.7898 meters. Now, it gives me a negative number, and the reason why it's negative is because my final position, or my final vertical position, is actually lower than my initial vertical position, and that means that the object has traveled down. So this negative sign just means my displacement is in the downward direction. But really what it's asking is how tall is the building? So this is going to be a scalar quantity. So how tall is the building? Well, the building is going to be 103 meters, which is like as tall as a, as tall as a football field, bigger than a football field. It's a huge building. But I have to look at significant digits. If I look, I only have 2 in this 4.6. So I need to take this 103.7898 and turn it into 3 significant digits. So my height of my building, h, is going to be, I can only have 2, so that's going to be 100 meters. All right. But in order to show 2 significant digits, it's going to equal 1.0 times 10 squared meters. Okay, so now I have 2 significant digits, and I can tell that the school's height is 100 meters. Now let's go ahead and move on to the next problem. So now we have a rock that is thrown up from a cliff with an initial velocity of 3 meters per second. If it takes 4 seconds to strike the ground, how high is the cliff and how fast is the rock moving when it hits the ground? So this is a 2-part question, so we'll work it twice. Now one thing that we need to know, and I want to go ahead and start off with this, is that whenever I throw an object up in the air, all right, there's some key points that I want to talk about. And that is that if I were to measure out horizontal segments, the velocities at these 2 points, so at this point and this point, are going to be the same. So those velocities are going to be the same. Same thing with the velocity here and the velocity at the starting point. Those will be the same velocities. And that has to do with the fact that gravity is accelerating the object constantly at a negative 9.8. And so as it goes up, it's slowing the object down. And so it travels up the same amount of vertical displacement. But as it comes back down, because it's going through the same amount of vertical displacement, gravity is working on it at the same amount of time. And so it speeds the object back up the equal amounts. So at equal heights in the path of an object, then the velocity of the object is going to be the same. Now obviously the direction is going to be different. One's going to be going up and the other one's going to be going down. But as it stands right now, that's good enough for us to know. When we start talking about 2-dimensional motion, then we'll start looking at those directions and exactly how they mean. So we have a rock that's thrown up from a cliff with an initial velocity. So that means I have an initial velocity, and it's 3.0 meters per second. And let's go ahead and make that 2 significant digits so that when it comes time to the end, I can keep 2. Now, this is going up because it's positive, and so that means that this 3.0 meters per second is up. And then it takes 4 seconds, which is a time, so time equals 4.0 seconds to strike the ground. How high is the cliff, and how fast is the rock moving when it hits the ground? So let's start with how high is the cliff. So that's delta y. And g equals 9.81 meters per second squared down. So now I'm looking for delta y again. And so this one does not have a delta y, so it's gone. And so let's see here. This one has a delta y, delta y, delta y. I do not have a final velocity, so all of these with the final velocities are now taken care of also. So this is just like the first problem, except now I have an initial velocity. And so I'm going to go delta y equals vi t plus 1/2 gt squared. In this case, I have 3.0 times 4.0 plus 1/2 times negative 9.81 times 4.0 squared. Now when you're filling this in, you need to take into account the importance of direction. And I know I said we'd get into more of it later, but I'm retracting that statement and going back. So you need to remember that anything that's going up or to the right is positive, anything that's going down to the left is negative. And so my initial velocity was going up, so it's positive, but my acceleration is pointing down, so it's going to be a negative number. And so if I look at this, my delta y is going to be 12 plus, and in this case 4 squared is 16, times 1/2, which is 8, and so I have 8 times 9.81, and I get a negative 78.48. So this means that the ball travels initially up 12 meters, and then it falls back down 78.48 meters. Okay, so I go ahead and do this number, and I get 12 minus 0.48, and I get delta y, or my displacement, or the height of the object, is negative 66.48. And if I keep two significant digits, this just becomes negative 66 meters. And so the height of the cliff is just a 66 meters. And we'll just say that because height is a scalar, I don't need to have the negative sign in there. And so we just know that if I were to measure the cliff, it would be 66 meters tall. Okay, so now we have the first part. And so let's go ahead and write this down here, that my delta y is negative 66 meters. And let's go ahead and get rid of all this nastiness. And we'll start all over. All right. So now I have my knowns and my unknowns written down already. Except for this last part, it says, how fast is the rock moving when it hits the ground? So I'm looking for V final. So, well, this one does not have a V final in it, so that one's out of the question. But now I have these other three problems, or other three equations that I can use to find V final. Now here's the key. This is a calculated value. Okay, and we've already talked about using calculated values in our problems. So this one is calculated, so anytime that I can get away from using delta y because I calculated it, the better. And so if I look here, V final, that's what I'm looking for. My initial velocity is a given, g is a given, and time is a given. So that one is good to go. All right. If I look at the third one down here, my final velocity is what I'm looking for. My initial velocity is given. G is given, but delta y is calculated, so that's iffy. And then same thing with this one, the delta y is calculated, and so once again that's iffy also. Because this first equation is all givens, that's the one I'm going to use to solve for my final velocity. So V final equals V initial plus GT. If I fill this in, I get 3.0 plus a negative 9.81 times 4.0. And so I'll go ahead and type that into my calculator. 3.0 minus 9.81 times 4.0. And I'm going to get my final velocity equal to negative 36.24. And with the two significant digits, that's going to be negative 36 meters per second. Or my final velocity equals 36 meters per second down. So both of these are accurate. All right, so there's our two example problems. I hope this helps you out on the homework. If you have any questions, feel free to let me know and I will help you out. This is Mr. Tompkins signing off.